Good afternoon. My name is Sandy Black. Thank you for joining us for the webinar today. All of NEL's webinars are sponsored by Bayes. Today's topic will be delivered by Cal McLaughlin on ultrasonic flow meters in flaring applications and their correction by means of computational fluid dynamics. Callum has been working for NEL for over 4 years and is one of our CFD experts and helps us deliver consultancy and research projects throughout the business. If you have any questions throughout the webinar, please put these into the chat and there will be a Q&A at the end. Callum, it's over to you now.
Thanks, Andy. So hi everyone, I'm Callum McLaughlin, and today I'm just going to be taking you through a few slides regarding ultrasonic flow meters in flaring applications and how we can use computational fluid dynamics to correct these flow meters. So for the agenda today, I'm going to be discussing what flaring is. I am also going to talk about what an ultrasonic flow meter is and why we would use one of these over another flow meter. I'm also going to briefly touch on what computational fluid dynamics is, and I'm going to show you a few examples of how we used CFD to correct ultrasonic flow meters. So I'm sure we've all seen something like this. So this is a flare stack with quite a chaotic flare at the end of it. And what I'm hoping to answer today is what this is, why it's needed, and what it's emitting. How we can measure the flow of gas in the flare stack, and hopefully answer some problems that these flare stacks cause. So first and foremost, what is a flare? Well, a flare, also known as a flare stack, flare boom, gas flare, is essentially just a pressure release device used to safely burn excess hydrocarbon gases. And these hydrocarbon gases come from the extraction of oil. So when you extract oil, you'll get the hydrocarbon gas, and sometimes you'll get water. And these are separated through the knockout drum. Oil and gas companies do their best to reuse and recycle these gases. However, sometimes it's not possible, and therefore we use the flare stack to get rid of the hydrocarbon gas. So these excess hydrocarbon gases are mixed with air and sometimes steam, and they're burnt off in the flare system. The reason why we do this is because methane, which is a primary component of the flare gas, is significantly more potent than carbon dioxide, which is an artifact of the combustion of the hydrocarbon gas. So gas flaring is used within a wide range of industries. It's not just oil and gas. So you can find them in wastewater treatment plants. You can find them in landfill sites. So landfills use them basically to get rid of the bad odour smells so they don't escape. However, you will primarily find these flares within the oil and gas industry. We also have this process called venting. And this is when we do just release the hydrocarbon gas to the atmosphere. However, this is done in low quantities. And we only do this basically for a quick release of gas so that the pressure in the system doesn't exceed the pressure of the pressure threshold of the pipework. So the first main purpose of a flare system is an emergency relief system. So as I said, you don't want this pressure within the system to exceed the pressure, the threshold pressure of the pipework, because if you do, there could possibly be an explosion, which is obviously a massive health and safety risk. This gas also has a low price, and therefore there's a low incentive from oil and gas companies to transport this gas, because when you compare the cost of basically transporting the gas, either through pipework or by trucks, and comparing it with how much you get back for the gas, there's obviously a low incentive to sell. Flares also may have routine shutdowns and maintenance periods. So an instrument may need to be swapped out for a new one, or you might need to rework pipework, and therefore you need to depressurize the system, and you do this through a flare. And as I said before, hydrocarbon gas is primarily composed of methane, which is significantly more potent than carbon dioxide. Therefore, the hydrocarbon gases is often combusted to create CO2. So, where is flaring found in? So, all these yellow and orange dots represents an operational flare on Valentine's Day 2021. So you can see that some countries are more populated with flares than others, and that's because 10 countries around the world make up 75% of the total gas flare globally, but only produce 50% of the world's oil. And this may be because some countries cannot reuse and recycle the gas as well as others, or maybe they just have more excess gas during the extraction of oil. However, 196 countries in 2015 agreed to help reduce emissions due to the importance of global warming. And this is important because in 2021, 143 billion metres cubed of natural gas was flared globally. And this, the CO2 equivalent of this is actually more than the total CO2 released from cars in Europe. So in recent years, flaring has come under a lot of increased scrutiny by the regulators, mainly focusing on making sure that your flare meter is accurate. And accurate flare gas metering is important because of a number of things. So first and foremost, reporting the correct number of emissions is the humane thing to do, as obviously it affects everybody. We then have hydrocarbon production. So hydrocarbon production can be limited by flaring, and what I mean by this is by increasing production, this would lead to the operator exceeding their flare consent. We then have sanctions and fines. So sanctions and fines can sometimes be applied to operators who exceeds their flare consent. So if you're flaring more than what you are reporting, you'll be receiving a sanction or possibly a fine, and this is very costly to the operators, so they want to avoid this. Now, with everything, there's obviously challenges in flow metering. So in the past, operators never really focused on making sure that their flare meter read within a certain uncertainty. Their main focus was making sure that the flare was operational due to the critical role it plays in safety. But with flow metering, there are obviously challenges. First challenge is that there's a large range in flow rates, and this ratio in flow rates between the minimum and maximum is called the Tundem ratio, and it can be as large as 1 to 10,000. Obviously, flares play a critical role in safety, and therefore, if there's an issue, you want to get rid of the gas as quickly as possible. So you want a flow meter that will provide a pressure drop of preferably 0 pascals, because if you have an issue, you want to get the gas out as quickly as possible, and if you have an intrusion within the line, that is obviously stopping or preventing the gas from moving as quickly as possible. A lot of meters can only be calibrated based on ideal conditions, but as you'll see later on, this is not always the case with flare systems. So most of the time, flow meters will be installed in non-ideal conditions. The meter is often located just after. The meter is often placed just after the knockout drum, and from the knockout drum you could have oil droplets or water droplets, so you need to make sure that your meter will not be affected by liquid drops. And finally, the meter is often placed in difficult locations, therefore it's hard to maintain. So you're basically wanting a meter that's not got any moving parts, because obviously maintaining those meters will be difficult because it's placed in a difficult location. So let's have a look at the widely used flow meters in the industry, and why we don't use some of them in flare systems. So firstly, we have the Coriolis meter. So this is a mass meter, so it directly measures mass and can also directly measure density. However, these meters usually provide a small Tundem ratio and are intrusive, and therefore it's not applicable to flare systems. We also have the turbine meter, and these are a velocity type flow meter and work on the principle of magnets. Now, as you might expect, turbine meters have blades and are therefore intrusive. Again, that's not what we want, and we also need to regularly maintain these meters because either supply the meter with oil, or you might need to carry out an oil service to make sure it's operating in tip-top condition. We also have differential pressure meters. So this might be a Venturi meter, might be a cone meter, it might be an elbow meter. So we have seen a few elbow meters within flare systems. However, we usually do require a large upstream length with these differential pressure meters, and sometimes they need to be calibrated quite frequently. We then have a vortex meter. So these meters work on the principles of vortex shedding, and as you might expect, they might create vibrations within the meter, and these vibrations might induce a high uncertainty in the meter readings. These vibrations may also cause reliability issues too. We then have electromagnetic meters, and this requires a conductive fluid for these meters to work, and therefore they're only really suitable for liquids, and they also tend to be quite expensive. So again, obviously, since we flare gas, these meters aren't exactly suitable. And finally, we have the ultrasonic flow meter. So this is a volumetric flow meter that operates on the transit time philosophy, and we actually use these flow meters within flare systems. And this is because of a number of things. So it can handle the large range in flow rates. There's no moving parts with this flow meter, and therefore, there's these meters do not provide any sort of intrusion in the line, and therefore provide a very small pressure drop. These meters can be calibrated based on ideal and non-ideal conditions. And there's no moving parts within this meter, and therefore it's not hard to maintain. So if it's placed in a difficult location, that's perfectly fine. In addition to this, the meters can also be applied to a wide range of pipe sizes. You can get a clamp-on version or a wetted version. You can also use these meters with gas or liquids, and you have the option between the transit time technique and the Doppler technique. However, the transit time technique is only really used because it provides a lower uncertainty. So with the transit time technique, you have two transducers, and each transducer can transmit and receive an ultrasonic signal. And basically, the time each signal takes to travel from one transducer to the other is measured. The distance between the two transducers is called the path length, and the axial distance is called the axial length. So if there's no flow, the time it takes for the signal to move downstream and the time it takes the signal to move upstream is the same. But with the additional flow, the time it takes the signal to move downstream is quicker than the time it takes the signal to move upstream. And this is because if you think about when you're swimming and you're swimming with the current, it'll be much quicker to swim with the current than against the current, because obviously you have that resistance of flow. And that's the same scenario here. The gas that's moving is resisting the flow from the signal moving upstream. So this difference in time between upstream and downstream is calculated, and the difference in time is then directly proportional to the flow velocity. You can then calculate your volumetric flow rate by multiplying it by the internal area of your pipe, and then as a result you can get your volumetric flow rate. So these ultrasonic flow meters have a couple of configurations. Firstly, we have the mid-radius configuration. So this is when the probes are inserted parallel to each other and are usually inserted at the depth of half radius. Sometimes it can be a full radius, sometimes it can be a quarter radius, but typically it's about half radius. We then have the diametric flow meter, and this is when the transducers are inserted at an angle with respect to the axis of the pipe, and the manufacturer who's designing these flow meters dictates what angle this is. With both the mid-radius and the diametric meter, you can have multiple transducer pairs. So as you might expect, as you increase the number of pairs, the accuracy of the meter increases. However, obviously, if you increase the number of pairs, the cost increases too. So with flow meters, your result will essentially be affected by installation effects. And what I mean by installation effects is when the flow is disturbed by certain disturbances within a line. So this might be a bend, might be a T-piece, might be a thermal, might be a branch. And to get minimum uncertainty in your meter readings, you require a fully developed flow profile. And manufacturers recommend that you install these flow meters, so ultrasonic flow meters in particular, with 20 diameters of undisturbed upstream flow and 5 to 10 diameters of undisturbed downstream flow. So the meter is designed and calibrated to work with ideal installations. So the manufacturer would expect a fully developed flow profile like the one on screen there. Once they have this flow profile, they can then calculate their correction factor, also known as the K factor. So the K factor is essentially just the actual flow rate over the measured flow rate. So if your K factor is less than 1, your meter is overreading. If your K factor is greater than 1, your meter is underreading. They can then plot this K factor, creating a correction curve, and usually manufacturers would supply operators with a single K factor. So across a range of Reynolds numbers, the K factor would stay constant. However, from our analysis, we have seen that when the meter is installed, the velocity profile would actually look something similar to this. And you can also see that the velocity profile of the as installed condition is not the same as the ideal condition. And in actual fact, it's quite different. Through our analysis, we've also seen that the K factor changes with Reynolds number. So obviously you can then see that the factor of K factor is not sufficient, especially at the higher Reynolds numbers. So how can we correct these flow meters then? Well, we've got a few issues with correcting these flow meters. Often the flare gas meters are installed in difficult locations and are therefore difficult to remove. If you can remove them, it would cause significant downtime for the asset, which is obviously undesirable. These meters can also be up to 60 inches in diameter, and the velocities can be as high as 150 meters per second. So finding a facility that can operate with these conditions is quite unlikely. Even if you can find a facility that can operate with these conditions, the flare systems are usually 100 meters in length. We've actually seen some flare systems that are kilometers in length. So replicating one of these flare systems would be cost prohibitive, really. Therefore, the only real practical way of correcting flare gas meters in situ is to use CFD. So, CFD, or Computational Fluid Dynamics, is a powerful modelling tool used to predict the detailed three-dimensional behaviour of liquid, gas and particle flows. So it's usually split up into 3 different stages. So first you have your geometry, and this is where a client would supply you with a CAD, and you would essentially extract the fluid volume from this CAD. You then move it into the mesh solver, and this is where you discretize that geometry and you create subdomains. And these subdomains are often called cells, elements, finite volumes, and the collection of these cells is called a mesh. And each cell reports a value of pressure, velocity, and any other physical property that needs to be calculated in the solution stage. In the solution stage, you would pick your turbulence model. If it's a turbulent flow, you'd pick a laminar model if it's a laminar flow. And essentially, you would run the solution to convergence. Once you have convergence of your simulation, you then have your result. So if we look at a simple CFD example, we can see here we've got a straight pipe with an inlet length of 337 diameters. We've then got our meter installed, and then we've got 15 diameters of undisturbed downstream length. And the flow is obviously moving from bottom to top. And we're going to compare the results with another set of results where we've got a case with a bend. So we've got the same inlet length, we then have a bend, and then we've installed the meter as per manufacturer's recommendations. So in both cases, we are going to be using a single path diametric meter, and the velocity range is going to be ranging from 10 meters per second to 35 meters per second. So looking at these results then, for the case with just a straight pipe, taking the velocity profile at the location of the meter, we can see that the velocity profile is as expected. There's obviously no disturbance in the flow. And so, yeah, the velocity profile is as we expect. When we look at the case with the bend, we can see that the velocity profile is actually skewed to the left-hand side. So on the left-hand side of the pipe, we are seeing that the velocity is much higher than what it is on the right-hand side. It's just purely because of the bend. So the bend is creating swirl flow, which is disturbing the flow as it moves through the flow meter. So we take both of these flow profiles, we put it on a simple 2D plot of a flow meter. For example, like this one, we can draw the meter path like that, and we can zoom in on where the flow profiles are, where the meter is reading the flow profiles, and we can see that there's a slight difference. So this slight difference actually corresponds to an 8% difference in K factor. And this is purely because of the lower velocity for the case with the bends, resulting in an underreading for the case with the bend. And this is actually a good example of when an operator believes that their flow meter is overreading, or the flow meter is not disturbed by flow disturbances. So when an operator believes that they are overreading, but they're actually operating at their minimum purge, then they are leaving themselves open to fines and sanctions. Okay, so if we have a look at a real life example of an operational failure, we can see that the operator decided to place the meter 27D away from the nearest disturbance as opposed to placing it elsewhere. What we've done though is we've had a look at the K factor for various different locations, so 1D, 5D, 10D and 20D away from the closest disturbance, which is the bend. Because usually when you're building a failure system, you have an option to install the meter somewhere, but usually this is dictated by accessible, how accessible it is. So this operator decided to use a single path mid-radius meter. So what these K factor results are showing is that the actual K factor changes with position. So we need to understand the installation effects. So for each K factor result, the meter is seeing different parts of the flow profile because of the swirl that's created upstream. So you can see at 1D, the meter is clearly affected by the swirl compared to the K factor at 10D and where the meter is actually located. So depending on where the meter is located, it will sometimes see high velocities and it will sometimes see low velocities. So we also did the same, but for a single path diametric meter. So using the same simulations, we extracted the K factor. And you can see that regardless of where the meter is located, the K factor is biased based on where the swirl is within the pipe. So you need to understand where the meter will be located, why it's best suited there, because installation effects are present even in this simple geometry, and they significantly affect your meter readings. The only way really to get around this is to use multiple paths. So one path may be under reading, but the other path may be over reading. But they essentially cancel each other out, and the meter is not affected as much by installation effects. So looking at another operational flare, in this case the flow is moving from bottom to top, and in this scenario we have valves and pressure related devices upstream of the meter, which is located there on the flare boom. And this operator decided again to use a mid-radius single path meter. And looking at the configuration of this meter, we can see that when we're moving with the flow, the meter path is located on the left hand side, and the upstream transducer is located in the upper section of the pipe, and the downstream transducer is located on the downstream section of the pipe. So operators prefer to see a simple K-factor curve because it means that there's not much chaotic flow within the flare system. However, for this example, we actually saw quite a chaotic curve, so it's not consistent at all. And in actual fact, the difference between minimum and maximum K-factor is around 18%. So this obviously took an interest with us, because usually we don't see these sorts of things. So we took two cases with quite a similar flow rate. So you can see that the actual flow rate is about 1.4 for case 1, and for case 2 it's about 2.3. But the absolute error in the K-factor is quite significantly different. So when we're looking at the results, we can see that for case 1 the flow was rotating clockwise, and for case 2 the flow was actually rotating anti-clockwise. So there's a different rotational flow, and you really wouldn't expect that, especially if you know, obviously in this case the geometry isn't changing, it's just the process conditions. So that's quite an interesting point, which is why we're looking at these two cases. So if we have a look at how the meter is configured again, the meter path is located on the left hand side of the pipe, and the upstream sensor is located in the upper part of the pipe, and the downstream sensor is located on the bottom side of the pipe. And to understand the difference between the two cases, we can plot the tangential velocity at the start of the meter path for both case 1 and 2. We can also plot a simple 2D version. Obviously the meter path is essentially 3D, but we can plot a 2D version of the meter path onto the contour plot. And we can see that the upstream sensor's there and the downstream sensor's there. Now the arrow on both of these contour plots dictates the rotational flow, so hopefully you remember for case 1 it's flowing clockwise, and for case 2 it's flowing anti-clockwise. So if you think about the meter path, the path starts at the top on the left hand side of the pipe and moves downwards. This geometry of the path therefore means that for case 1 the flow is moving away from the meter, but for case 2 the flow is moving in the direction of the meter path. Therefore the path in case 2 is continually affected by the swirl of the flow. And it also happens to be for case 2 that the swirl is strongest at the point of metering, therefore affecting the meter readings even more. So to summarise this slide and the previous few slides, the rotational flow can really impact your meter readings depending on the geometry of the meter path. And this is something that's difficult to quantify if you were to use a facility, but it's something that's beneficial through the use of CFD. So we have created a significant number of ultrasonic flow meters and flaring applications over the years, And what we've seen is there's no significant difference between mid-radius and diametric meters. You can see they overlap quite nicely when you plot them on a k-factor and Reynolds number plot. The only real difference is that mid-radius meters tend to be installed in larger pipes, and diametric meters tend to be installed in smaller pipes. And this is because when you have a diametric meter in a larger pipe, you need more power to push the signal from one side of the pipe to the other, especially when you have a higher velocity. We've also not seen any significant difference to k-factor curves if the meter has been installed as per manufacturer's recommendations. So you can obviously see that the results, again, overlap quite nicely, despite the fact that they're split up to be installed correctly and installed incorrectly. So regardless of the installation, there's no real sign to say that one is better than the other, and therefore we would recommend correcting these meters. So just to summarise the past few slides, flaring is an essential safety device which is used to remove excess hydrocarbon gases produced from the extraction of oil. Because of new emission targets and regulations, this has created a requirement for flow meters to reach within a defined uncertainty. Ultrasonic flow meters are the most utilised flow meter within flare applications due to their versatility and low uncertainty. The manufacturer's calibration of ultrasonic flow meters is not sufficient due to the complex pipework. And computational fluid dynamics offers the flexibility of correcting ultrasonic flow meters while also not impacting production at flare sites. So thanks very much, guys, for listening. If you have any questions, please feel free to put them in the chat and I'll do my best to answer them. I think you're on mute there, Sandy.
I'm just seeing. Oh.
There you are.
I don't think I am.
There you are. You're good.
Can you hear me?
Yep.
Good stuff. Good old technology, eh? Yeah, just saying thank you for the presentation, Callum. It was very, very interesting. I'm just waiting for some questions to pop in. There's a few here. Yeah, I'll fire some questions at you then. So I've got one here. How do you find the right installation? Presumably that means from your ultrasonic meter. How do you know it's installed in the right place?
Yeah, well, there's no right or wrong installation, to be honest. So what the CFD has revealed to me is that the manufacturer's recommendations do not fully guarantee a fully developed flow profile, especially in such installations where you have multiple bends and disturbances upstream of the meter. And obviously these disturbances and bends will create a disturbance in the flow profile. So at higher Reynolds numbers, you'll likely have persisting swirling flow, and the flow profile will pretty much not always be fully developed. So the message here is even if the manufacturer's recommendations is respected, you still really need to calibrate your meter to see what effects the disturbed flow has on the meter. Hopefully that answers that question.
Good stuff. Good. I think it does. Here's another one. This has been asked a few times. It seems quite open-ended, but it's quite an interesting one. What do you see as the future of flare metering? So, what do you think is going to happen in the future? There's a lot of focus on emission measurement and control. What do you think? What do you see as the future of it?
Well, as I said earlier on, there wasn't much focus on making sure that the uncertainty of the meter was as small as possible. Operators really only just focused on making sure that the flare was operating correctly because of the vital role it plays in safety. But obviously with stricter regulations coming in, there's a real focus from operators to make sure that the flow meter is as accurate as possible, because if not, they could possibly be fined, or in some cases they could be sanctioned, which is obviously not what the operator's looking for. So I think manufacturers will probably look to replace the current setup with meters that have multiple paths, so maybe that's 4 paths, 8 paths, or they'll look to calibrate the meters correctly using tools such as CFD. But also with that, with the significant rise in machine learning recently, I think coupling CFD machine learning together will allow operators to calibrate and verify their flow meters in real time. So that's what I think the future of flare metering is, to be honest. It's quite an interesting part that's getting looked at more.
Yeah, I agree. It looks like it's going more towards the fiscal route now. So yeah, interesting times. Looking at the time, I think that's probably all we've got time for today. So Callum, I'd like to thank you again for an excellent presentation, and for future events and webinars. There'll be email communications from our marketing department, and you can also find that on our website as well. So thank you for everybody's time. Thank you for paying attention, and thank you for all the questions. If I've missed any questions, I'm sure Callum will follow up on them in due course. So thank you very much, and have a fantastic rest of your day.
Thank you.